related, I hope. It's something related to scattering amplitudes. In quantum field theory and string theory. Okay, so let me start by giving you some references. So these are lecture notes. So this is a classic. So almost everyone has learned from here until a book came out. But it's still on the archive. So the book. So Selvan one. Wait. Oh, that's much better. Okay, 1697. Good. Very good. So let me try to motivate you a little bit for why you should sit here throughout these 3 weeks and suffer and do all the exercises and all that. So most of us do theory, but most of us also want to connect to experiments. And
sorry to interrupt, but can you quickly adjust the microphone so that it's on the outside of the shirt, not on the inside?
Yeah, but there is a parity problem here.
Yeah, the other one was just on the inside.
I know, but it's a weird.
You can rotate the.
Okay, that explains everything. Thank you. Okay.
Perfect.
All right. Of course, that shows that I'll never be able to make experiments. However, I do theory. And I can still compute something in between to give to experimental, okay? And that would be the scattering up. So where do we use this? So we have the Large Hadron Collider. This is a big ring, 27 kilometers across. So we have 2 beams of protons being accelerated in different directions, and they are made to collide at different locations where we have detectors. So this is a proton-proton collider. And we have hundreds of billions of protons colliding every second. But what do we see, or what are we interested in? So we have a proton coming in, another proton coming in. And many of the interactions we're interested in is when we have 2 gluons coming, colliding, and producing other gluons, which then decay and produce something else. Okay? So let me see if I remember how to use this. Very good. So we will have collisions of the form 2 gluons producing 2 gluons, 2 gluons producing 3, and so on. You would say, well, so what? That's not such a complicated thing. After all, we know how to use Feynman diagrams. Feynman solved completely the problem of how to compute these scattering amplitudes. So we all have to thank Feynman for his diagrams. But let's try to just see. I mean, most of us, when we take quantum field theory, we do first scalar field theories. And when you take quantum field theory too, hopefully most of you did some Young-Mills calculations, right? Okay, very good. So you probably did a 4-particle, a 4-gluon Amplitude, maybe. No? Okay. Some of you didn't. Like, but those of you who did, so let's do a little bit of combinatorics to see what the problem is. So if you remember, you will have a cubic coupling in Young-Mills. You would also have a quartic coupling. Now, this cubic coupling, when you write it down, what it looks like, it has 6 terms. This one has 3 terms. And also, depending on how you count. I mean, this is 3 terms are grouping the thing a little bit into pieces. But if I really expanded this thing, I could count it as 6 terms as well. Now, what are Feynman diagrams? Let's consider the case when we have 4 gluons interacting. So meaning 2 in and 2 out. So what are the Feynman diagrams we have to consider? So if we give labels to the particles 1 through 4, then the combinatorial problem that we have to address is the following. We can choose one of these guys to be the root of a tree that is growing, but this tree is only allowed to do 2 things. It's only allowed to grow 2 branches at the time or growing 3 branches at the time. So these are called binary ternary trees. So this guy will grow 2 branches or 2 branches here. So that's something that it can do. How many of these kind we have? Well, depending on which particle comes out here, we will have something like this, we will have this, or we will have this. So we have 3 diagrams of this form. But we could also have a tree that grows and grows 3 branches. And we only have 1 diagram of this form. Now, if you want to compute how many terms will you have when you actually carry out the calculation, so the rules are very, very simple. Feynman told you, write down the Lagrangian, which we're going to do very soon, find the Feynman rules, draw Feynman diagrams, and then just keep going. But as I told you, every cubic coupling has 6 terms. So each one of these guys will give you 6 squared. This guy, I'm being generous, I'm saying we can multiply just by 3, and this is around 100 terms. Even the 2 to 2 scattering is 100 terms. How about the next one? For 5, what do we have? So we have these diagrams. We have this diagram. We have diagrams like this, and so on. So you can check that there is, I did the calculation, so we have 15 of these diagrams. So we have to do this times 6 cubed. And these ones, we have something like 10 diagrams of this form, times 3, times 6. And this is roughly 3,400 terms. Okay? So you will probably see these numbers. Many people write them. And they say that for 4 particles, we have 4 diagrams. For 5 particles, we have 25 trees. So we're only drawing trees at this point. And for 6 particles, imagine the number of terms that you actually have to write down grows way faster than the number of diagrams. But even the number of diagrams grows very fast, and this is 220 trees. Okay. But if you're a theorist and your experimentalist friends, they tell you, look, we're building this collider, you have to compute this thing. Otherwise, we won't be able to make predictions. Then, well, what do? There's nothing to do but to do it. And that's what Park and Taylor did in 1986. They did exactly these calculations. And they found, so they did this 4-particle and this 5-particle calculation all the way to the end, and they found a miraculous simplification. So they found a miracle. Yeah, let's leave it at miracle. I was going to write miraculous simplification, but so they found a miracle, and that's the reason why the amplitudes for which they found this miraculous simplification, where you write pages and pages of answers and they collapse to something very simple, are called Park-Taylor amplitudes. So one of the goals of this course would be to discuss these Park-Taylor amplitudes. Now, this is only a very small subset of all possible amplitudes that appear in Yang-Mills theory that we have to compute, or that our experimentalist friends with access to compute. Okay? So people, after seeing this miraculous simplification, they try to find the same miraculous simplification in other amplitudes, and they didn't find anything. So this was left as a miracle. Now, in 1988, Nair decided to study this little miracle and try to reinterpret it. And he found that these Park-Taylor amplitudes could be thought of, and that perhaps was the reason why they were so simple, as correlation functions on a sphere. But not just any sphere. It was a complex manifold. Do you know the difference between any regular sphere, like the basketball that we use to play, and a complex sphere? So what would be the difference? Both are spheres. Topologically, they are both spheres. But what makes one of them a complex manifold and not the basketball that we used to play? Anyone? So what do you think? That's the sphere that he found.
Is it something to do with point and infinity?
Well, that's just the way you parameterize your sphere, but you're going in the right direction, which is that if you have a sphere, you can choose to parameterize it by using the stereographic projection onto the plane. But on the plane, we're very used to introducing complex coordinates, right? So if you use complex coordinates and you attach complex coordinates to your sphere, then you turn your sphere into a complex manifold. Of course, you need two charts in order to cover the whole sphere, but the space of different spheres with different ways of attaching coordinates to it defines the space of these complex manifolds. So this is the one that he found, and this complex manifold has a name. It's called a complex projective space of one dimensions. And he found that this thing not only looks very nice, but it had appeared already in a physics context. And it turns out that this CP1 is nothing but the celestial sphere. When you go out at night and you have a look at the stars, what you are seeing is a complex manifold. It's a celestial sphere. And the reason is that a Lorentz transformation transforms the coordinates for the location of the stars just as a holomorphic transformation would on this complex manifold. And Penrose was obsessed with complex variables. I don't know if you know that, but he loved complex variables. But we all do, right? After we see the miraculous things that happen when you have complex manifolds or complex numbers, you would say, well, if nature was complex, everything would be very, very easy. But then you look around and you say, well, we have 3 space dimensions and 1 time. How can we make that complex? It sounds impossible. But looking at the sky, you say, well, there is hope. There is something that is a complex manifold out there, and maybe we should push and try to build an object associated with space-time that has this complex structure. And that's what he did. And this thing naturally lives in a higher dimensional space, which is called twistor space, which is the space of null rays in space-time. So our space-time is not complex, but the space of all possible null rays gives you something very nice, and that's the twistor space of Penrose. Okay, that's all very good. This was very beautiful. But then you would think that that's the end of the story. This explains the miracle. So there is no miracle anymore, and you don't do anything else. And that was the story. Ah. It's not working, right? One of the presets is not. Really?
The front board just doesn't work at all.
Okay, so oh, the top one doesn't work.
Yeah.
No, the front one is not working, right? Okay. Yeah, that explains the phenomenon. Okay. Okay, so that was the story. And people went on to compute these amplitudes, putting them on computers, and whatever computer they had, they computed more and more things, more power, more memory, more power was needed, and all that, until in 2003, Witten said, there is also another place where we use CP1s all the time, where we use complex spheres, and that's string theory. Could there be a connection between string theory and this object that Nair found? So Witten constructed, or he decided to mix twistor space with the string theory and constructed twistor string theory. Now you know what the string theory is, so you took a course on string theory. But what is this twistor string theory? Well, it's a joke. Nobody knows what the string theory really is. I mean, that's the whole point. That it's a non-perturbative thing, blah, blah, blah. We don't know. It has many, many branches. Maybe it's really M theory. So we don't. But in any case, this twistor string theory is called a string theory because it's also a theory about the space of maps from a sphere into some space, and that space is twistor space. Now, we also know that when you compute a string theory is not supposed to give you quantum field theory amplitudes. It's supposed to give you something much more complicated. But this twistor string theory is a special one where you are actually computing a string theory. You're actually computing quantum field theory amplitude. So let me be more precise in what I mean by that. So in quantum field theory, we take, say, our gluons. So here it is. This is a gluon. And we have Feynman diagrams. We have a gluon carrying some momentum P, interacts with the others, and you produce Feynman diagrams, something like this. Now, in string theory, what do you have? Well, you don't have a point particle that travels. What you have is a string that travels. So it generates this picture, and many strings can combine and produce other strings. So this one can come and join another one and produce other ones. So you have some strings that are coming in, some strings that are going out, like we had some particles here. But now you see that this picture, we couldn't tell if this picture is computing this or if this picture is computing this. Why would you think that this one is computing something similar to this or something similar to this? It actually seems to be computing both at the same time. And it's actually doing so. So this single diagram is computing not only the sum of these diagrams, but it's actually deforming quantum field theory into a much bigger object. So this whole thing contains these diagrams as limits. as limits of what? So a string theory can be thought of as a deformation of quantum field theory. But if it's a deformation, we need a deformation parameter. What is that parameter? That I'm sure you know. What parameter do you think we have to tune to turn a string or to make a string look like a particle?
Tension?
The tension, exactly. So what's the limit?
High tension? Infinite tension?
Infinite tension, yeah. So the strings have a tension, and we want infinite tension. The tension, for historical reasons, is computed in terms of something called alpha prime. I won't explain what alpha prime is. I mean, you should know. I mean, from the historical way string theory was derived. But this is just a dimension-full parameter that has dimensions of what? Of length squared, right? So this length is called the string length. So we have the string length. So what's the limit in which a string will look like a particle when the string length goes to 0? So quantum field theory should be recovered when alpha prime goes to 0. Okay? So this week and next week and so on, well, not this week. This is the last time we're going to mention alpha prime, I mean, at least this week. But the following 2 weeks, alpha prime will start to come back. And this is what you're going to hear all the time. There is alpha prime. Now we're introducing alpha prime. We're expanding in alpha prime. And we want to connect to field theory when alpha prime goes to 0. Okay. Very good. So what is the outline of the course? There will be 3 parts separated naturally by weeks. So the first part is going to be about quantum field theory. And in this part, we're going to discuss techniques, new techniques for calculating these amplitudes in an efficient way. Techniques for efficient calculations. But there is also a chance of not just being a good citizen to the world and to your experimentalist friends by developing new techniques and clever ways of doing things so that they compute things faster. But these techniques have come attached to reformulations. Of at least perturbative quantum field theory. So every time you have a reformulation, there's something very useful, perhaps, or potentially useful, because it allows you to think about the physics behind the phenomenon in different ways. And sometimes you might discover something very unexpected. So the classic example that, I mean, we all like to explain, to give to people, is the reformulation of classical mechanics. So when you go from Newton's equations to the Lagrangian formulation, you would say you didn't gain anything. It's just a reformulation. So have you gained anything? Well, we have. So there are many things that become clear in the Lagrangian formulation that are not completely clear in the Newtonian formulation. But even more so, the Lagrangian formulation is telling you that there are all these, when you do the variational principle, there are all these other solutions that are not the solution exactly to the variational principle. And could they have any physical meaning? Well, at the time, people said no. But later on, we know the end of the story. So the same thing could happen with these reformulations. So it's also useful to have. So in week 2, before we go to week 2, so these reformulations will come into 2 different classes. We will have a geometrical and a combinatorial one. In this geometrical one is where we're going to discuss the twistor string theory. Or reformulations related to it. Now, as I mentioned, this twistor string theory doesn't have any alpha prime in it. So no alpha prime. There is no alpha prime. So mysteriously, this is a string theory that computes quantum field theory amplitudes. So in the second week, we're going to see how this twistor string theory can be reformulated even in a more natural way. If you think about a different space that is not twistor space, this is called ampli-twistor space. And the reason this space is going to be nicer is that after having this formulation that doesn't have alpha prime but looks like a string theory, you're itching for a way of connecting this to string theory. Could there be any way of introducing alpha prime? And this is actually the better way, the best way we have so far of doing it. I have to confess, I'm not completely satisfied with the way we are going to introduce alpha prime, but that's great. It means that there is still work to be done. So ampli-twistor space and turning on alpha prime. And last, after we have alpha prime, at the end of next week, we have a string theory, and it will be string theory amplitudes. But not from the standard point of view. Here, too, we are at the stage where people are finding, in fact, the person who's going to teach this third week is one of the people who found this thing. I cannot believe, I cannot remember. Mira. I think this is correct. So they have found some miraculous phenomena, which at this point in time, they are still miraculous things. So we are back full circle. We are back to full circle in the sense that now we have again something that is completely miraculous and we don't fully understand. And this miraculous phenomena is related to new mathematical connections. Okay? All right. Good. So I was half of the lecture just introducing what we're going to do in the lectures. That's a little too much. Now let's actually do something today. So where do we start? Let's So let's start with the theory that we want to study. Okay, so I'm sure I can assume that you're all experts in Yang-Mills theory and how to quantize it and all that, right? Well, but it doesn't matter because we're not going to do it that way. So that's the good news. So the Lagrangian, what's the Lagrangian? Well, we can always start with a Lagrangian for Maxwell theory, okay? So we start with the Lagrangian for Maxwell theory. This is something that we know and love. Okay? Now, Yang-Mills theory is nothing but a theory of a bunch of photons that are allowed to interact with each other. Okay? So we need an index to tell us which photon we're looking or we are treating. Right? So we're going to introduce some number of photons. So this is an object that is going to characterize which particle we're looking at. Okay? So we sum over all these guys. I'm not going to tell you how many we're going to have. And the way they interact is by just allowing them to talk to each other through numbers that will determine who is allowed to interact with whom, and a coupling constant. Which I invite you to have a look now, because I think I'll never write it again. Okay? So from now on, G is going to be 1. So any other G that you see in these lectures is not the coupling constant, it's something else. So this is the first time and the last one that we're going to write it, and this is our Lagrange. Okay? Now, I already convinced you that if we follow Feynman's rules, we're going to crash. There will be a combinatorial barrier, and we won't be able to make any progress. So we have to completely change ways of thinking. We have to find new tools. And the first one we're going to discuss today is called color decomposition. So white color, well, this index A is what people call as color. And it is based on a group structure, which we're going to take to be UN. So this is a group of unitary m by m matrices. Why do they form a group? Well, take any two unitary m by m matrices. Well, let me remind you what unitarity means here. That the inverse of the matrix coincides with this dagger. So if you multiply any two elements of this group, you get another unitary matrix. So just matrix multiplication gives you a group structure for this object. Now, if you have studied quantum mechanics, from the point of view of quantum information, you know that people are obsessed with unitary matrices and how to study them and write them down and the space of unitary matrices. But if that were extremely trivial, then all this quantum information thing would be extremely trivial. So unitary matrices, studying that group is not that simple. But there is a trick that we can use to study it. What is the trick? Instead of studying unitary matrices, we can study something else, which is slightly simple. What are they? If we write them like this, instead of studying unitary matrices, we can replace that problem for the problem of studying what are T's. What kind of matrices are they? So this is our trick. If we want U to be unitary, what do you think T has to be? It's an m by m matrix that has to be yes?
Hermitian.
Yes, exactly. Hermitian. Excellent. Very good. So instead of studying this space, which looks complicated, we're going to study the space of Hermitian matrix. Now here what's going to happen is that we're going to think about the space of unitary of Hermitian matrices as a natural vector space structure. Why? Well, because you can take a unitary matrix, multiply by a real number, and it's still, a Hermitian matrix, you multiply by a real number, is still Hermitian. You can add up Hermitian matrices, and they are still Hermitian. So Hermitian matrices behave like a vector in a vector space, where the field that we are using to define the vector space are the reals. So that all sounds pretty good. So we can choose bases for our vector space. How many? What do you think is the dimensionality of this vector space? Last chance. It's n squared. We need n squared vectors to span the most general element in this vector space. But I'm going to write this as follows. One of those elements is the identity matrix. That also is a Hermitian matrix, right? So I'm going to choose it and separate it from the rest, and you will see why in a second. This U is union, not unitary. Okay, so we have these guys. Maybe I should tell you why I'm separating this right away. So what are the unitary matrices that I can get from this one? So we look at the formula. We say, well, you can take this element and multiply by any real number that I'm going to call for no reason whatsoever, phi. Right? So I'm going to take this identity matrix and multiply by a real number phi, multiply by I and exponentiate it, and produce this guy. But this is nothing but this. So this is the group. This is actually a subgroup of this group. And it's the group of just bases. We can multiply them. And there is an inverse. Phi equal to 0 is the inverse, produces the identity. Minus phi is the inverse of this. So this is all a subgroup of that. And this subgroup is called U1. Why U1? Because it's the group of 1 by 1 unitary matrices. This guy. And it sits inside the bigger one. Now, what are these ones? Well, this part is called SUN. And we have discovered this is SUN because these are the ones, the S means special, and this means that these guys, well, it doesn't look that they are special, right? Because actually this one looks more special. Right? But in any case, that's the name is given. It's called special because the determinant of those matrices, of these matrices U, is supposed to be 1. Okay? So this matrix here violates that condition. The determinant is not equal to 1. And these ones are chosen so that the determinant is equal to 1 for the ones that you generate. Very good. And that's why these are called special. So we have just discovered that UN is the product of two groups. Of course, in nature, N only takes 3 values so far. But here, we're doing theoretical experiments. So we're allowed to take N to be anything. So we're going to take N to be any number. All right. So these lectures go until 3, right? More or less? Excellent. Good. Okay, so we have these guys. Now, how do we study this group? This group is very complicated, as I said. So instead, we're going to study the algebra. We're going to study these Hermitian matrices. So the group structure. So what happens to the product of two unitary matrices is all encoded. Well, you all know this famous Baker, Campbell, Hausdorff formula, right? From the time you were studying spins and quantum mechanics, right? Well, this formula tells you that in order to know what the product of two matrices do, if you write them as the exponential of another matrix, all you have to know is all the possible what? Commutations, relations between the two elements that define this and this, and all the nested ones, right? So all this information is encoded in these commutators. So instead of studying this, we can just study this. And now if we multiply by an I, this guy can be thought of as a product in the space of Hermitian matrices. What do I mean by that? Well, we had a vector space, and now we're giving a way of multiplying vectors. So we can say an element in the vector space times another element in the vector space, which I now define as this object, clearly can be expanded in my basis, right? It also belongs to the vector space. So a vector space endowed with a product is called what? An algebra. So instead of studying the groups, we can study the Lie algebra of UN. And that's what we're doing. Very good. So to understand the whole structure of the algebra, all we have to understand is what the generators do. So let's take any two generators and hit them with each other, with this product. So let's take the generator TA1, TA2, and compute the commutator. So the commutator is nothing but the product of these two matrices, n by n matrices. So this one times this one minus this one times this one. So the failure to commute is going to be something interesting. And that failure to commute can be expressed again in terms of the basis, because this is a basis for all Hermitian matrices, and this is a Hermitian matrix. So we should be able to expand this in terms of the basis. And all the algebra structure is given in these numbers, which is not an accident, are exactly these ones. Okay? So the way our gluons are allowed to interact will be only through these guys. Okay. Now our basis can be chosen. We can normalize it, right? Like we do with any vector space. We can choose it so that TA times TB, if we multiply these two elements here and we take the trace, this is simply a way of computing. You can think about this as computing the norm of the object, okay? And we're going to define this to be, well, strictly speaking, I should put the half, but just like the coupling constant, this is the first time you see it and the last time you're going to see it. So I'm not going to write that half anymore. And the reason it's good to normalize it that way is that now after performing that normalization, we can write the structure constants, the Fs, in terms of these matrices. How do we do that? Well, we're saying that this guy can be expanded in terms of these bases, but we can project, we can get the coefficients by using the norm, right? By using something that projects onto the different spaces. And the way to do it, again, the same phenomenon of disappearing will happen to this I. Okay? So somehow the I's, that half, the G will disappear. So how do we get A1, A2, A3 from that formula? Well, all we have to do is to take this A1, A2, hit it with TA3, and compute the norm of that thing. We compute the trace, and that gives the structure constants. Now let me expand this out. If at any point you're not clear with a step that I'm doing, please let me know, right? Okay, so we're expanding this commutator to get TA1 times TA2 minus TA2 times TA1, but the trace is linear, so I can separate these two objects and write this like this. Okay? Now we're going to introduce, so far this lecture has been extremely boring, but now we're going to introduce pictures. So hopefully it's going to be a little bit more exciting. So let me introduce a pictorial representation for all these things. So these matrices are m by m matrices. So every time you see something like this, the first and the second index, we will have to distinguish them. And we're going to say that this, or we're going to represent it as follows. We have a line that corresponds to A, and the first index will go into the matrix, into here, and the second one will go out. Okay? So just for fun, as I said, we have to make the lecture a little interesting. So let's write down the norm, this trace relation over there. So what do we have? We have trace of TA, TB, but this is the same as IJ, TB, J. We're multiplying the matrix and then taking the trace. So we also have to make the last index the same, and we are summing the indices, right? These indices are sum. Okay, how does it look like? Well, it looks, we have A, and then we draw our thing here. We have I going in and J going out. And this guy looks now like B. And then we have J going in into B and I going out. And it would be extremely, extremely hard not to connect these lines. And connecting the lines means to sum over. But the identity tells us that if we have this, all we have is AB. So this will be a representation for the delta function. Right? Our identity over there. Oh, yes, of course. Sub. Okay, now something more interesting. Let's represent this guy in terms of the pictures. How about that? What would they look like? Well, let's start with this one. So let's start. So our F, A1, A2, A3 is going to be equal to this trace. But now, as you see, the indices will be IJ, JK, KI. So it's very easy to draw it. It's going to be a circle where you're going to have A1, then I going, it's going to meet A2, A3, and it's going to go to A1. Do you agree with our rules for the pictorial representation? Excellent. Now, this would be this minus, what do we have? Now we have A2 going into A1 and going into A3. So our structure constants are nothing but the sum of these two terms. So hopefully this, yeah. All right, so now let's try to apply that to amplitudes. And we landed on precisely the correct blackboard, because now we want to apply these two Feynman diagrams. I know we said we didn't want to draw any Feynman diagrams or do anything like that, but well, we have to start from somewhere. So let's see if these pictorial representations will allow us in any way to do something better with the combinatorics, or to at least use the idea of divide and conquer in order to simplify what we have to do. So this cubic coupling for Feynman diagrams is something that comes in the Lagrangian from multiplying the term with two a's with a term that has a derivative and an a, right? So this thing comes with a derivative of a, but for the time being, we don't care about all this part. So this will translate into some metric with derivatives of momenta and so on. But for the time being, we don't care about that part. We will worry about the kinematics tomorrow. Today, we are only interested in what comes here, the f. There is only one f that comes with these guys. So this diagram will come together with our f. How about this diagram? Where does it come from? This diagram, or this vertex, comes from the product of two terms of that FAA times FAA. So this diagram will come with two products of f. But at the end of the day, everything are just structure constants. So let's start with this diagram. What do we do? Remember, we have no idea right now what to do with the kinematic part. So we are going to strip out the kinematic part. Everything that has momenta, metrics, derivatives, and all that, everything, we're going to do it tomorrow. Today, we're only interested in what happens to the color structure. So I'm going to draw the color structure in the following form times the kinematics. So we're going to have A1, A2, A3, and A4. This is something that you should know from your quantum field theory 2, that every time Feynman found an internal line, he told us that to have unitarity, we have to sum over all possible states that you have in your theory that are available to you to run in that line. So that means that every time you see a line like this, what we mean is that there is an index P, and that index P is summed over all possible values it can possibly take. But that's great, because that's also how we are treating lines here. Every time we join a line, we sum over all possible values it can possibly take. So this P goes from where to where? From 1 to n squared. And we're summing over it. And for the time being, we don't care about this part. Okay? So let's actually make the transition to the full pictorial way of doing things. How am I going to represent this? Well, let's represent it like this. So the structure constant, or the interaction at the cubic vertex, is going to be something that can be expanded in this way. So let's do that for this object. As I said, we're only worried about the color structure. So let's expand this. We have one cubic coupling here. So I'm going to expand it. So it's A1, A2, B minus A2, A1, B times this one. So I'm expanding this guy here. Now I'm going to expand this by using my rules. It's B, A3, A4 minus B, A4, A3. And I'm supposed to multiply and sum over B. Okay? Let's see, I think we can. And for the final trick of today, we just want to simplify that. So what do? We just hit each term with each term, and we're going to get 4 terms. So it doesn't sound like a good improvement. We started with 1 term, and now we ended up with 4. Sometimes things get more complicated before they simplify. So we get this thing is going to be 4 terms. Let's look at the first one. What's the first one? It's A1, A2, connected to A3, A4, plus minus the other terms. Okay? Now, the last trick is that we have to use that this vector space also has a completeness relation. And what's a completeness relation? It tells you that if you sum over all elements in your vector space, you get the identity. What's the identity in this space? It's this one. Now, if you look in the standard quantum field theory books like Pesky and Schroeder, and you look into the Appendix A, you will find this formula with an extra term in it. Who is right and who is wrong? Of course I'm right. Well, we're both right, because we're computing different objects. This is a completeness relation for UN, and in the book, they are considering the completeness relation for SUN. Now you can see why I decided to stick in this U1, because it makes, if you look at the extra term here, it looks complicated. But putting in the U1 part simplifies the formula. Now let's write this in our pictorial representation, and we're going to be done with what we want to do. So how does this look like? Well, we are experts now. So this looks like this. We have I and J, I going into A. That's this thing. And then on the other side, we have K is going into A, and L is coming out. But the relation says that this is equal to our delta functions over there, mean lines connecting the 2 labels. So I and L are connected. Very nicely, the arrow flows from one side to the other side, and this one is connected like this. Okay? Now let's apply that to this part of the diagram. It's exactly the same thing that we have. Now we just applied it, and this thing becomes, we have A1, A2, A3, and A4, and this object, what it's doing is fusing these 2 circles together and inducing an ordering. Plus 3 more terms like that. Just like this one. Now let's go back to the trace representation. So what could this possibly be in terms of our generators? We want to go back to what they look like. So this object, if we want to write it, well, first of all, it has to be a trace because we are summing indices. This is T, A1, with an index ij, but j is contracted with the index for the element Ta2, but this the leftover index is contracted with Ta3, and that one with multiply with 4, and the last index is contracted with the first index here, which means that we're doing a trace. So this diagram is nothing but a trace of all these generators. Okay? So what have we discovered? We have discovered something that is called, let's see, actually, the color decomposition. So every Feynman diagram will give contributions that look like this. And now what we do is to collect every kinematic factor that has the same trace structure. So our 4-particle amplitude, whatever it is, which we don't know how to compute yet, calligraphic, that's very important. You have to use calligraphic for this, eh? It's not a joke. You will see why. What we do is write this and putting here all the possible kinematic junk that comes together with these factors. Every time you find one, you dump it into here. Now, there will be another trace with a different ordering. And every time you see this trace, whatever kinematic thing that comes in, you dump it into here, and so on. So this kinematic junk is the purpose of these lectures. So that's the thing we want to compute. And these guys are denoted as partial amplitudes. You see, it was important. And they depend on an ordering. Which ordering? This ordering that you have. This one will be 1, 2, 3, 4. And now your exercise would be to prove at all 3-level amplitudes can be written as follows. So you choose a permutation Sn is a group of permutations of n elements. Zn is a group of cyclic transformations. Now, you will have until I finish writing this formula to decide or to figure out why I'm modding out by Zn, why I don't want to overcount something. So here we have the 8th omega I or omega 1 element. So I apply the permutation to the element 1, and whatever I get, I put it here. And I have the product of all these things times the corresponding object. And this object has a name. It's called a partial amplitude. And if you feel, so for a bonus question, do this, find the corresponding statement for one loop amplitude. All right. So we're done with the color decomposition. Thanks. So I'll see you tomorrow, and then tomorrow we are going to do kinematics. And with the kinematics, we will be able to find what these partial amplitudes are.